Hello friends, today we're gonna be discussing this question from LeetCode, which says, the name of the question is determining if a cell is reachable at a given time or not. So what does the question really ask us to find? So here will be given four integers, sx, sy, fx and fy. These are basically coordinates. These two are coordinates and these two are coordinates. And a non-negative integer t. You are given an infinite 2D grid. This term has to be is given importance here, infinite, which means there is no end of this 2D grid. You start at sx or sy. You start the given point here, this point, and each second you must move to any of the adjacent cells. And here adjacent means that you can move in any directions. Like for this, you can move here, 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 here. So 8 directions, right? So 8 directions are there if you observe it carefully. So you can move it in this way. Now what do you want to find? You want to return true if you can reach to fx fy after exactly t seconds starting from sx sy, and false otherwise. What it is saying is if you can reach from sx sy to fx fy in a given time frame of t, exactly t is important here, then you need to return true, otherwise false. Very simple explanation to the question. Now let's take some look at some examples here to better understand what does it really mean. So for this particular test case, we are given like sx equal to 2 and sy equal to 4, fx equal to 7 and fy equal to 2. So basically we want to go from 2,4 to 7,7 with time 6. So there is this one way given, like you can start from start and then you will go from this way, like this is 1, this is 2 seconds, this is 3 seconds, this is 4 seconds, this is 5 seconds, and then 6 seconds exactly you reach to your final destination. So this is how you can do this. Now, so it is possible for this case, like, so that's why we have returned true. Let's look at the next example. We want to go from 3,1 to 7,3 from here to here. In number of steps equal to 3. So if you see here, like this is the way we have approached the taken to reach to finish. And as you can see, we didn't find any way from this starting position to this finishing position from where for which the length of the path or the amount of time taken for that path would be 3 or less, 3 or would be exactly 3. We couldn't find such a way. So that's why we have written false here. There is no path. If you try to go from this way, if you go travel from the here to here to here to here to here to here, it's like 1 second, this is 2 seconds, 3, 4, 5 and 6. 6 seconds are required, but here the time frame given is 3 seconds only. Let's try another way. This 1, 2, 3, 4, 5. At most 5, at minimum 5. So at minimum we are requiring like 5 seconds. Okay, so we couldn't find any way which could get us from sx sy to fx sy in a time frame of 3 seconds. So we need to give return true if it is possible, otherwise return false. So how can we approach this question, or how should we approach this question? Okay, now one thing which we need to think of is like what are the possible ways to do this. Like when you see such a grid, the most common thought which comes into an individual's mind is to use something called BFS. BFS does it like you can travel in 4 directions using it, or in any of the directions you want to, like. So we come across this thought of BFS, but do you really think we need to do BFS here? Is there any need of doing BFS here? Why and why? Why so? Why am I saying this? So if you see that from a cell, and if you see the entire question, you are given that you can revisit the same cell several times. What does it mean? Like this is the state from where we start. According to BFS, we can go to its corresponding states, adjacent states. So we go into these states. Now these states can again go into this state. Okay. And this will further go down to the respective other states. the concept of visited is not being applied here. The concept of visited is not being applied here, and that's why the complexity which would come by using BFS is going to be extreme. You can assume it your own now. Like you start from. So what if I like, let's take for a moment that we decided to go for BFS. So what we would do? You would start with the initial node x comma y, and you would keep a variable time t, and you would go down to its respective nodes, like one node here, one respective neighboring nodes or what we call as cells here, and then you would increment here by one, like t plus 1, t plus 2, t plus t, and at every moment in the process you would check whether the t1, whether this particular index is equal to the final destination or not, and if it is, you would further determine whether this t is equal to the t given in the question or not. So you can see that this can work, this will work for sure, because BFS is we are traversing through all the ways. But the thing is, do we really need to do this? Do we really need to travel all the ways? Okay. Do we really need to travel all the ways? Because if we do it, you know that the complexity is going to be very, very high. And it's going to be extremely huge tree if you go from BFS. If you go using BFS. So what I am saying here is, let me just erase it first. Okay. So let's break down this question into segments. So we are given a starting node, starting position, okay, and ending position. Let's say it is x1 y1 and x2 y2, and the time frame to reach from starting position to ending position is t. Now think of this way, like if the minimum amount of time that is required for us to reach from starting position to ending position exceeds this amount of time, then will we ever be able to reach from starting position to ending position in time t? If the minimum, there can be multiple ways now. I told you, like you can go from this way, you can go to this way, you can go from this way to this way, this way to this way, this way to this way. You can go from this way to this way. There are multiple ways to go from starting position to ending, starting position to ending position. But if the minimum of all of these paths is still greater than t, then there is no way we can reach to ending position in time t. So we can simply return false for this case. Yes or no? Completely yes. Okay, we can simply return. So one thing is done. If minimum time, and how will we figure out the minimum time? It is very, very simple. Then you must return false. Just keep this in mind for a moment, and we will look into how we can find minimum time. Okay. Now another condition is if minimum time is equal to 2, then you obviously have found the way to reach from starting to ending in time t. So you will simply return true. But there is another case that comes in your mind, that what if the minimum time is greater than t? Is lesser than t, or we can say if t, the available time is greater than minimum time that we require to reach from starting node to ending node. What can we do in that scenario? Okay, so let's try to explore this case individually. So we know that our time is greater than minimum time. Okay, so which means I need to have I want to create a grid here. Okay, so there we have it. So let's say we want to move from this position to this position. Okay, and the amount of time that we are given is 6, for instance. So what we will do is, what is the minimum amount of time? So the minimum amount of time is like if you go from this point to this point, then this point to this point to this point, you will reach it. Okay, so the minimum time is 3 seconds. Okay, so which is lesser than this t. So we have some extra time remaining. So what do we have? We have some extra time remaining. Okay, so how our purpose is to utilize that extra time. We have some extra time now. What is the extra time here? The extra time that is available to us here is 6 minus 3, that is 3 seconds. So we need to capitalize this extra time. We need to use it in some way so that our purpose of reaching from starting position to ending position in time t is satisfied. So how can we do this? So one smart way of thinking is, let's start from the starting node. Let's go and stop here. Okay, we reached here, we went from this point to this point, from this point to this point. We reached here. Now how many points, how many seconds are we left with? We are left with like, it took us 2 seconds from here to here, from here to here. So we are left with 4 more seconds. And one will be to travel from this side to this way. So at most we can utilize 3 seconds. But now we have 3 further seconds which we need to waste, ultimately, so that this is satisfying. So what we can do is, we will travel in its neighbor. It is no significance, but to utilize those extra seconds we are doing it. So 1 second will be utilized in traveling from here to here, and then again coming from here to here, so 2 seconds were utilized. Now there is 1 more second left. There were 3 extra seconds. Now there was 1 more second left. So what you will do is, you will travel into this side, this way, and so 1 more second utilized. Now this. So can you see a pattern? Wasn't that intuitive? Okay, let's take a very specific case. Like if minimum time. Okay, so if t minus minimum time is equal to 1, which means that there is a 1 extra second. So let me just, no, okay. So I have 1 extra second, okay. And this is my starting point, this is my ending point. I reached here. Now I have 1 extra point to waste. What can I do? If I go from here to here, the number of seconds which it took us will be 3. But I want 1, and so 1 more second will be left over. So I want to utilize that, or I want to waste it being in the question frame. So what I'll do is, I will go to one of the destinations adjacent nodes. I will stay here. I will come to this point, no issues. But then I will not directly jump to the destination. I will jump onto one of its adjacent nodes and then go from there to the destination, so that I can waste that 1 extra second that I have. Okay, I thought that you were able to relate it with what I'm saying. So let's take another example, like if t minus when time was equal to 2. So in this case, we have 2 more seconds to waste. Okay, so destination was here, na? So I reached from here to here, I am here. Okay, now how to waste the 2 seconds that I have? How to waste those 2 seconds? So what I'll do is, I go to one of these nodes. I will travel from here. I will go from here. I will travel to here. And then I go from here. Then, let me explain you again. Okay, so our destination is here, our source is here. So what I'll do is, I'll come to this point. So for that, I'll be taking 2 seconds. 2 seconds are being utilized here. And I have 2 more seconds. So that I have 2 more seconds left over to waste. So what I'll do is, when I'm here, I will go to this node, and I will come back to this node. So when you go from a node to this node to this node, 2 seconds are required. So you will waste those 2 seconds. And once you are here, you can go to the destination then. So you will be having 3 seconds. So the concept here is, waste the extra time. Waste your extra time. Okay, waste your extra time. We have covered both the cases for like t, when the extra time is 1 and the extra time is 2. For any of these values, for any value greater than minimum t minus, if the difference, for any difference of these 2 entities to be greater than 2, or equal to these two values, we know that there exists some way of wasting those times. Okay, so this is possible. So we can simply return true for this as well. Simply return true. When the difference between the time given and the minimum time is greater than or equal to 1, we can still return true, because we know that we have got some way to waste that time and keep that under the constant of t. Okay. But now there is an edge case. What edge case is this? What edge case are we going to discuss now? The edge case is, what if the starting point equals the ending point? You will be asking, how is this an edge case? And t is equal to 0. Okay, and t is equal to some, and t is given to us. Okay, so we are initially at the starting point and we want to reach it at the same point. Okay, so let's say the time that is given to us is 0. Okay, in this case we know that 0 seconds are given to us, and because we are already at the end point, so we can simply return true, no issues. What if 2t is equal to 1? Okay, this is the starting point, this is the ending point. But you have 1 second. You need to waste this 1 second in a way that at the end of this, you need to utilize this 1 second in a way that at the end you are at the final destination. Is there any way? Is there any way you will get out of this cell and reach to the same cell again under a time frame of 1, given that every operation takes 1 second? Every movement takes 1 second. I didn't mention that, but every step that you take just takes 1 second. In each second you must move to any of its adjacent cells. Okay, so starting point is equal to ending point. So is there any way you can say that if I start from 1 and end up at 1 after having 1 second? There's no, because if you go anywhere else, like there you will say there's one neighbor here, there's one neighbor here, there's one neighbor here, there's one neighbor here, I can go to this one. But this will take 1 second. But when you will be returning, you will not be having any other second left, because it will be turning 0. You will not be having any other second left to reach from here to here again. So there is no way for you to travel from starting point to ending point when both of these are equal and t is equal to 1. So for this specific case, you will return false. Okay, and what if t is equal to 2? That is very easy. Like you will go to any of its neighbors. There are 8 neighbors. You will travel to this and you will come back. You will travel to this and you will come back. So t equal to 2 will be utilized, and at the end you will be at the final destination. So these were the test cases which you need to keep in your mind. Edge cases which you need to keep in your mind. Otherwise it's a maths problem. It's an intuitive problem. Maths problem, a bit you can say thought-provoking, but very easy to execute. So let me just show you the code for it now. Okay, so initially we were given, so we are checking that edge case which I explained you just now, that if both the final destination is equal to the ending destination and t is equal to 1, we discuss this. So in this particular case our answer will be false, because we won't be able to utilize 1 second in a way that we end up in the final destination starting from the final destination. So we will simply return false. In any other case, this is the way, like this is the difference between the x coordinates of final and initial destination, and this is the difference between the y coordinates. And what is this thing? What is minimum steps? You don't need to do it. You can simply initialize min steps with this particular value. Sorry for being redundant here. So in case what do you know? You know that let's say we are given a coordinate 1, 4, this is source, and destination given is 3, 3. So what are the delta x? 3. What is the delta x? 3 minus 1, 2. And what is delta y? 3 minus 1 2. Okay, so you are here and you want to go here. So what is the minimum number of steps that you need to take, and which will obviously be equal to the minimum time as well. So you can, because you are allowed to go diagonally, you will move here to find the optimal time. You will move in this direction. So it is basically saying that only, that if you, so the minimum time will be nothing but maximum of this two values, del x and del y, because del x means covering the horizontal distance and del y means covering the vertical distance. So the maximum of these two values, like whatever the amount of time that it will take for you to cover this distance and cover y distance, the maximum amount these values will obviously be the time taken you to cover taken by you to go from source to destination in the minimum amount of time. So basically this is what we are doing here. The minimum stage is nothing but the maximum amount dx and dy, which will basically represent our maximum time. Are you able to understand this? I think so. So we are checking the way simple condition that if the minimum number of steps required are greater than t, then there is no way for us to reach from the source to the destination in time t. Okay, so we will simply return false. Otherwise, for every other case, we have figured out that the answer will be true, so we are simply returning true. So what is going to be the time complexity for this particular code? So the time complexity is extremely simple. It is going to be big of 1, because we are not utilizing any loop or any such thing which requires some time complexity of more than constant. So, and the space complexity is obviously of 1 as well. So that's all from my side. I tried my level best to make you explain this code and make you explain the intuition behind this logic. And if you could understand this, please like this video and do comment in the comment section. And if you think that I can improve at some points, then do mention that in the comments. That will be really helpful for me, because I'm in the initial days of teaching, so I will be making some mistakes, and that's where you are here to point me out. So your feedback is extremely important. So thank you for watching this video till this end, and if you have watched this, please like the video, share the video, and if you can, please subscribe the channel, sorry. Thank you. I will see you in the next one.